Okay, so first, for Bernal equation, this is another type of first order ordinary differential equation, okay, this is our last type for this chapter before we proceed with the application. Okay, so the general form is given by dy dx equals to bx y equals to cx times y to the power of n. So as you can see here, it is quite identical with what? What can you compare this form with?
Linear equation.
Yes, it is quite identical with linear. Okay, so for linear, remember, we just have dy dx plus pxy equals to qx. But now for Bernoulli, we have dy dx bxy equals to cx times y to the power of n. So this y to the power of n will represent the Bernoulli equation. So this kind of form is how can you identify the Bernoulli equation. And n cannot be 0 and n cannot be equals to 1. So in order to find the solution of this Bernoulli, we need to reduce to a linear because it is quite identical with a linear. So we have to reduce to linear by using the substitution of z equals to y to the power of 1 minus n. Okay, so first, how can we find the solution? Divide the equation with y to the power of n because we want to reduce that yn there. So now it becomes y to the power of negative n by dx plus bx y 1 minus n equals to cx, right? So differentiate, second one, differentiate the substitution equation with respect to x to get dy dx. So this one, we differentiate to get our dy dx. So z becomes dz dx. Y to the power of 1 minus n becomes 1 minus n y minus n dy dx. So from here, just simplify to get your dy dx there. And then what you can do from here is to substitute, to replace this 4 into 3. So we just substitute, right? And then what we can have here is now it become linear equation, right? So it is now a linear equation where you have your px, you have your qx, while the coefficient of dz dx here equals to 1. Now, once it is linear, then we just can proceed with solving the linear equation. We have to have the integrating factor and then substitute to the mu xz, integrate mu x qx then you can find the solution. All right, clear? Okay, let's take a look at the example. We want to solve okay, so now, as you can see, this is Bernoulli because we have y to the power of n there, where n equals to 4. Okay, identify your n first, n equals to 4. Second step, divide with y to the power of n. So divide with y to the power of n. So here we have 1 over y to the power of n equals to 4 dy dx plus 1 over 3, 1 minus 4y minus 3 equals to EX. So this one becomes okay. Then since n equals to 4, our substitution becomes z equals to y to the power of 1 minus 4, which is z equals to y to the power of y minus 3. Okay, and then what? And then once you get your z here, you differentiate, right? You differentiate with respect to x, you will have dz dx equals to minus 3y minus 4 dy dx. So from here, y minus 4 dy dx becomes minus 1 over 3 dz dx. And then substitute to this. Okay, so substitute y minus 4 dy dx now is minus 1 over 3 dz dx. Right. Plus 1 over 3 y minus 3 becomes 1 over 3 z. Right? Equals to e to the power of x. Then simplify in order to make the coefficient becomes 1. So you will have dz dx minus z equals to minus 3e x. So now, is it linear? Is it linear or not?
Yes.
Okay. So this, the coefficient now becomes 1. This one you have z, you have minus 3x. So what is your px and qx? So since this is linear, so you have to identify your px and qx. What is your px here? Okay, so px is minus 1. All right, qx. How about qx?
Negative 3 exponent.
Negative 3 exponent x. So this is your px, this is your qx. Now you know that this is linear. So what is your next step?
We solve for mu x.
Sorry?
We solve the integrating factor. The mu
Yes.
x.
So we need to find your integrating factor of mu x, which is mu x equals to exponent to the power of integrate px with respect to x. So we have exponent integrate minus 1 dx. So we have exponent to the power of minus x. Okay, so once you got your integrating factor, then just substitute to here. mu x, exponent minus x, z, qx minus 3 exponent x. So, you should have what? This one becomes minus 3 x plus c. So, z becomes, do we need to solve for c? No, because there are no conditions given. So this is how you find the solution of Bernoulli. First, identify n, okay? And then divide the equation with y to the power of n. And then use substitution for z equals to y to the power of 1 minus n, and n is 4, so you have the substitution z equals to y minus 3. Once you got the substitution, so you have to differentiate and simplify and substitute to the differential equation given. Once you substitute, then you can reduce to linear and then identify the linear equation by identifying the qx, the px, the qx, and make sure the coefficient of dz dx or dy dx that equals to 1. Then proceed with finding the integrating factor. Okay, and this is z, right? So remember to substitute back. What is z again? Z is y minus 3. So y equals to, z equals to y minus 3 ex minus 3x plus c. Alright? Clear?
Yes, Radha.
So this is how you find the solution of Bernoulli equation. Okay. Anyone has question? No question? Okay, let's try. Pass your question. Try to answer question number 2 here. Okay, by looking at the steps there, understand the question and try to find the question here. Using z equals to y to the power of minus 2, show that it can be transformed to linear differential equation. So just reduce this Bernoulli to linear and find the solution. Right. Okay, I'm going to leave you around 15 minutes. Try to find the solution of this first. Right, so we have done with the first one. is separable, right? Then we proceed with homogeneous. Okay. The difference between separable and homogeneous is just the usage of y equals to vx substitution there. Once you substitute, then you need to solve again the separable. Okay, and then for z, okay, it is quite different compared with this the previous two. Where you have to have m and n and find the solution for u. There are two methods for finding u there. Okay. And then we have linear equation where you need to have integrating factor. And then for the last type is for Bernoulli. It is related to linear, but you need to reduce to linear first by using the substitution of z equals to 1 minus n. So basically, as you can see from these five types of differential equation, linear and homogeneous are relatable. Okay, and sorry, separable and homogeneous are relatable, and linear and Bernoulli are also relatable. Okay, and then for a z, there are two types of method of finding the solution for a z equation. So this z equation is quite not related to other types, but it is doable, right? By using the differentiation process where you have to find the value, the solution for u. Okay. So there are 5 types of ODE there that you have learned. Okay, so as for now, let's proceed with the application of first order ordinary differential equation. Since next week we're going to have holiday on Sunday, right? So let's just proceed. Okay, so the first application is the Newton's law of cooling. Okay. Oh. We have how many applications are there? Okay, we have 4 applications. Okay, Newton's law of cooling, natural growth and decay, electric circuits model, vertical motion, which is Newton's second law of motion. Okay, so let's just proceed one by one. All right. So now let's take a look at this application. We have Newton's law of cooling, which is given by dt equals to minus kt minus ts, where k is a constant, okay, and ts is the constant temperature. As you can see, what is the type of the differential equation here? Right? We have the big T dash, the temperature. We have T dash, the time. So this is temperature. This is time. This is constant. And Ts is constant temperature or room temperature. Okay. So can anyone has an idea what is the type of this differential equation? Anyone? We have 5 types. Separable, homogeneous, exact, linear, and also Bernoulli. So what is the type of this differential equation representing by Newton's law of cooling here? Yes, it is separable. Okay. As you can see, you can separate T and T there. Okay, there is no small t here. So you just can separate the function here. So by putting 1 over t minus ts with dt and minus k with the small t there. Then this is separable differential equation, where if you want to find the solution of separable equation, you just have to integrate both sides. Okay, where this one you can have ln t minus ts, and this is minus kt plus with c, right? So omit the ln there, then we have what? T minus ts equals to exponent minus kt plus c, where you can write exponent minus kt times exponent c, then T minus ts is actually ae minus kt there. Okay? So your t can be written as ae minus kt plus with ts. So this is the solution of temperature here. Okay, if the initial condition is given, then we can find the value of A. Understand or not? Any question? Okay, by looking at this application, why don't we try this example? All right, according to Newton's law of cooling, the rate of change of the temperature, so the rate of change of the temperature, where temperature change within time, okay, you know that the rate of change of the temperature itself is defined by temperature change with time, so dt over dt, satisfy the condition of this Newton's law of cooling, where Ts, the ambient temperature, K is a constant, and T is time in minutes. When object is placed in room temperature with 10, okay, it was found that the temperature of the object drops from 90 to 30 in 30 minutes. Then determine the temperature of an object about after 20 minutes. Okay. All right. So now determine all the information. We have room temperature, which is what? Room temperature is what? Okay, we have your Ts equals to 10. It was found that the temperature of the object dropped from 90 to 30 in 30 minutes. So initially, the temperature is 30. Okay, this one is when T equals to 0. And then when T equals to 30 minutes, then the temperature becomes drops from 90. Drops from 90 to 30. So initially it is 90. After 30 minutes, it becomes 30. Now we want to identify what will happen to the temperature after 20 minutes. Okay? And you know it is given by this Newton's law of cooling. We want to find, so for this case, we want to find T when T equals to 20. So we need to have T, which is given by this Newton law of cooling. So we have done with the solution of this by this one. So you know that T equals to AE minus KT plus TS. Okay. So now, from here, all right, when T equals to 0, T is 90. TS is 10. So from here, you know that your A equals to what? A equals to 80. Okay. Done with this first condition. Then, when T equals to 30, what will happen to the temperature? Temperature become 30. And you know your A already. T is 30. And from here, you can find your K. How can you find your K then? Can you find the K there? What is your K there? Anyone?
Uh, 0.046.
Okay, 0.0462, right? Try to normalize the usage of 4 decimal places in your calculation. Okay, your end answer can be 2 or 3 decimal, but during the calculation, try to use at least 4 decimal places, okay, to get the accurate one. All right, so that is your K. Now, the equation now becomes T AT exponent minus 0.0462 T plus with TS is 10. So this is the particular solution of this problem. So now our problem is to find the temperature after 20 minutes. So we need to just substitute what happened to this T when time is 20 minutes. So just substitute the answer. Then you got your T there. Okay? Clear? What is your T? Okay, 41.75 what? 41.75 degree Celsius. All right, good. So this is how can you apply the differential equation that you have learned. First, you need to identify this kind of differential equation follow which type. Is it separable? Is it homogeneous? Is it linear? Is it exact? Is it Bernoulli? Once you can understand the types, then you can understand the problem. What are all the informations given? Then you can find one by one all the variables and constant. Got the particular solution, and then you can find the solution. Okay, clear?
Yes, perfect.
Anyone has question? Okay, try the second question from your past year's question there. Just before midday, the body of an apparent homicide victim is found in a room that is kept at a constant temperature, 70 Fahrenheit. At 12 noon, the temperature is 80, and at 1 p.m. it is 75. Assume that the temperature of the body at the time of death was 98.6 and that it has cooled in accord with Newton's law. What was the time of death? See, you can be a forensics now by using the differential equation, right? Okay, try to find it. So by Newton's law of cooling, you know that it is followed by dt dt equals to negative kt minus ts. And we have find the solution of t, which is t equals to ae minus kt plus ts. Okay, how can you obtain this? By solving the separable equation here. Okay, I have explained to you earlier. Right, so now let's take a look. What are the information given there? Okay. So the constant temperature means what? The constant temperature is your Ts. Okay. At 12 noon, initial time. So we decide when T equals to 0, the temperature is 80. And then at 1 p.m., okay, so this one we use hour. When T equals to 1, after 1 hour, the temperature becomes 75. Right? So assume that the temperature of the body at the time of death. So time of death is unknown. The temperature is 98.6, which has cooled in accord with Newton's law. So now we want to find what was the time of death. So which hour that this body has died. Okay, understand the problem? So this is how you gain all of the information. Okay, understand one by one. Okay, and then followed by which type of differential equation, find the solution, and then you can substitute one by one all of the information. So now we can find the constant first, because we have here what? We have constant A, we have constant K. So in order to find the solution, we need to solve this constant first by using the condition given. Okay, when T equals to 0, temperature is 80. So this one is 80. K, T is 0 plus with 70. You know that your A is what? 10, right?
10.
Okay. And then now your equation now becomes T equals to 10 exponent minus KT plus 70. So next condition, when T equals to 1, after 1 hour, when T equals to 1, the temperature becomes 75. So 75, T equals to 1 plus 70. Then you can find what is what is K here? What is K? K equals to what?
0.6931.
Okay, 0.6931. So now your solution problem becomes T equals to 10 to the power of minus 0.693 T plus 70. So this is the particular solution of this problem. Then you can find the solution. Okay, when the body is 98.6, we can find what is the value of T there. All right, just the same process with finding K previously. You can find T. What is T there? All right, you got your T?
Doctor, I got negative 1.516.
Negative. Okay, what is the meaning by this? Look at the timeline. At 12 p.m., the body temperature is 80, right? And then 1 p.m. the body temperature is 75. Means that when the body is 98.6, it should be before 12 p.m. right? Okay, usually when someone is died, the temperature will decrease, right? So as you can see, you get T equals to minus 1.5. So at 12 p.m. it is 80. After 1 hour, it becomes 75. Means that at X 98.6, it can be about 1.5 hours before. So the negative sign here represent previous time, okay, before 12 p.m. Okay, so we estimate it is about 1.5 hours, well, 1.516 hours. So that is the time of the death, maybe around 10:30 a.m. So this is how you determine the time of death for this problem. Okay, clear now? Estimatedly. It is not exactly 10:30, but it is estimatedly around 10:30 a.m. Okay, clear? So this is one application of differential equation where we apply it to Newton's law of cooling. So by Newton's law of cooling, we just can solve the temperature, time of death, and so on. As you can see from your notes, you can see the types of example there. We have temperature of buttermilk, right? We have time of death, temperature of porridge, temperature of cake from the notes there. Okay, you can try. Okay, so let's proceed with the last application for today. Okay, which is natural growth and decay. Okay, so now natural growth and decay. As you can see, what is the type of differential equation there?
Separable.
Yes, it is separable, right? So this natural growth and decay model here for this differential equation type is another type of separable equation. Okay, where K is a constant, X can either be the size of population, number of dollars, amount of radioactive, and so on. Okay, so the problems can be seen in the application of population growth, compound interest, radioactive decay, drug elimination, chemical reaction, and for the current trend right now, we can use this kind of model. This is the basic model where you need to modify a little bit in order to use in COVID-19 prediction. So this is one type of model that we use in predicting the number of COVID-19 cases. But of course, we need some modification. But the basic comes from here, okay? Where we can call it as a population growth, the growth of virus spreading, okay? So this is another type of application for differential equation. Okay, let's see the example here. But before that, you know, this is dx dt equals to kx. We can find the solution by solving this using separable equation. Okay, so we have here equals to what? 1 over x dx k dt. Okay, then solving this, you get ln x equals to k plus c, x equals to exponent k plus c, and x equals to ae kt, right? Okay, now looking at this example. A certain city had a population, so this is a population growth problem, okay, of 25,000 in 1960. So in 1960, initially, so when we say initially, of course, we assume when time equals to 0, okay, initial value, the P there equals to 25,000. The population of time equals to 0 is 25,000. All right, and the population of 30,000 in 1970. So in 1970, when now time moved around 10 years, after 10 years, okay, the population becomes 30,000. Assume that its population will continue to grow exponentially at a constant rate. So you know it grows exponentially at a constant rate by looking at the solution of this population growth. X is proportion to exponent x. So grow exponentially at a constant rate. What population can each city planners expect in the year of 2000? So in 2000, T now becomes what? After
30 years.
30 years or 40 years? Looking at this one is
40 years.
10. So from the initial to here to T equals to
40.
40. So now we want to understand what is the population after 40 years. Okay. By following the model here, natural growth and decay, you know that the population change within time at a constant rate. Okay, so same with this model, but just change the variable. The solution becomes what? P AE KT. So P AE KT. When T is 0, P is 25,000. Then we can find A. A equals to 25,000. Right, this one is T0. Now, when T equals to 10, P equals to 30,000. So A is 25,000 exponent K T equals to 10. Then you can find your K. What is K? What is K there? 0.0182. Okay, so now can you find the population after 40 years? So we want to find the population at t equals to 40. So just substitute your A, E, K is 0.0182. Now T is 40. So what is your P? Five one 51773. Okay, so 51773.4. So let's just estimate around 5177 for population. Okay, clear now, everyone? So this is how we implement the population growth in differential equation. Right? Anyone has question for these two applications? Okay, so that's it. Let's start with two applications today. Okay. So basically we have done with the first week, last week for definition, basic terminologies, then solution of differential, initial condition, boundary condition. Then we have done with solving separable, linear, homogeneous, exact, and Bernoulli, and use substitution. So actually we are on week 2, but we are now done with application of Newton's law of cooling and apa tadi? Natural growth and decay. Okay, so next application, we're going to proceed with electric circuit, and also we have 4 types, right? And also vertical motion. Okay, we have another 2 applications. So next week on Sunday, we're going to have our break for first day of Ramadan. Okay, so and then in our second class, let's just proceed and finish with the application of first order differential equation. All right, so if you have no more question, I think we can stop here. Anyone has question?